Okay, hi guys. So today we'll be solving Leetcode problem, minimum difference in sums after removal of elements. So we're given an array nums consisting of 3 multiplied by n elements. So we are allowed to remove any subsequence of element of size exactly n from nums. So the remaining could be 3n minus n, that's 2n elements, and we will be divided into 2 equal parts. The first n elements belonging to the first part and the second n element belonging to the second part. So the difference in sums is called sum first minus sum second, and we need to return the minimum difference possible after the removal of n elements. So here you can take a look at this example. We have an array nums with 3 numbers. We can remove one number from it. So if we remove this, the first part could be this guy and second part could be this guy. We get 1 minus 2, that's minus 1. We can remove this guy and that could be 1. We can remove this guy, that will be minus 1. We remove this guy, it could be 2. So our 3 option, minus 1 is the smallest. So we return minus 1. And same for this guys. We have 6 elements. We need to remove 6 divided by 3, that's 2 elements, right? And there can be many options here. One of it is to remove this guy and this guy. So we get 7 plus 5 minus 3 plus 3 plus 8, and that's 1. So what's the intuition here? Basically we need to find a way to split the array into half, right? So there should be a partition point. And then we will split it into 2 halves like this. And then for each half, right? For each half, if the length of each half is actually larger or equal to n, that is a valid partition, right? And if it's a valid partition, for example, if we choose this guy, right, that's 4 elements, we need to remove 2 elements from it, right? And after that, we need to make sure that after we remove the 2 elements, the sum of the first half is actually minimized and the sum of the second half is actually maximized. That's how we are going to return the minimum difference possible between them, right? Because the result is basically the sum of the first minus sum of seconds. In order to it to be minimum, we need to make sure the sum of the first half is minimized and the sum of the second half is maximized. Okay, 2 things to conclude here. Sum of the first half is minimized, sum of the second half is maximized. And we need to try every possibilities of every partition point, right? So now, for example, we will run through this test case, right? If we try it with this guy, can we do it? No, because now if we choose this guy as a partition point, then the first half should contain at max 1 element, right? So one partition should have at least n divided by 3 elements. In this test case is 2 elements, right? So this guy cannot be a partition point. So we come to this guy, Okay, 7 plus 9, 16. Right, this guy can be a partition. So now we come to this guy. Okay, in order to maximize these guys, we need to remove the two largest value in these four values. That's 8 and 5, right? So now is remove the two smallest. I'm sorry. So 1 and 3, we have 13 here, and we have 16 here, right? So that's 16 minus 13, that's 3, right? If we choose 9 at the partition point, so we come here, 5 will be the partition point. Okay, so now as you guys notice, the first half now has 3 elements. We need to remove 1 element from it. So the objective is to actually minimize the value of the first half, right? So we need to remove the largest guy up here. That's 9, right? So we have the sums of 12. Now come to the second part. Okay, now the second half has 3 elements. That's 1 element more than 6 divided by 2, 3, right? So we need to remove 1 element, and we need to remove the smallest guy. That's 1. Now we have 3 plus 8, that's 11, and now we have 7 plus 5, that's 12. 12 minus 11 is 1, and we do it for every index. Okay, we do it for every index. So is there a technique that we can use to actually like, how can we do it in an efficient way, right? So the brute force way is to actually do prefix sums, and then up to that point we need to find the maximum, the next maximum, and vice versa, and then minus it, right? And that should be not efficient enough, right? That should be somewhere, it should be something like n squared, if you know what I mean. So we can use prefix sum here, right? But in order to actually be efficient, we need to store the value of every number in a heap and then keep popping out from it, if you know what I mean. So here, I'm at index 1, I have the current sum of 7. I'm at index 2, I have the current sum of 7 plus 9, right? So now I'm at index 3, I need to remove 1 guy out of it, right? So you can imagine that we have a heap like this. Now we are at index 3, right? We need to remove 1 element out of it. We add 5 into this guy, right? And now we need to remove 1 guys, right? What are we going to do? We need to pop out from this heap, right? And then we need to pop this largest guy out, and we need to minus that guy, right? And then whatever is the result from this guy, we call it n. We use it, we plus the new guy in, and then we minus whatever the largest guy in the heap. That's 8. We call it as n1 plus 1. Now whatever is the largest guy here, we need to minus him, right? And now we have a prefix sums, but it's not a normal prefix sum. It's a prefix sum that tells us at index i's, right? What is the smallest sum? What is the smallest sum of all the elements with index smaller or equal to I, right? Of n element with index smaller or equal to I, right? Okay, so now that's one part of the solution. We need to do it in a reverse way, right? We scan left to right. Now if we come here, we choose 8 at the partition point, we need to know what is the largest value of an element with index larger or equal to the guy next to it, right? And then we will take this minus this, and then we get the value if we choose that guy at the partition point. Okay, so we will do a double scan, have a prefix and then the suffix. The prefix at index I tell us okay, so prefix at index I tell us what is the minimum sum of an element with index smaller or equal to I, and then the suffix at index I tell us what is the maximum sum of an element with index larger than or equal to I, right? Okay, so now we will do another scan. Choose partition point. For example, if partition point is index j, then the minimum difference will be prefix j, right, minus suffix j plus 1. Okay, so I hope you get the idea, right? It is pretty straightforward. Okay, so now we are going to implement it. So we need to have an array of prefix. Let me turn off this unique key. A suffix, and then we need to have a q, I in range, n, right? Basically that you push this guy into q, whatever is I, hit push q nums I. And then now we need to make sure the first half is the sum of the first half is actually minimized. So for each hip hop, we need to pop out the largest number, right? So in order to do that, when we push into the queue, because the queue, basically the default of the priority queue in Python is actually min heap. So we need to minus these guys, right? So now we turn it into the max heap. Okay, heap push q minus num I. Okay, so if so, when is the exact time that we tell the algorithm that we should remove an element from our prefix. Okay, so example, now here's 6 number, right? So one partition should have 2 number. So if one partition have 3 number, which is larger than 2, right? we need to remove one element from it. Okay, so if I plus 1, which is the number of element, is actually larger than n divided by 3, correct? Then we need to do prefix I minus 1. Prefix I will, so now whatever we pop out of the Q will be a negative number, right? So we just need to do this. We pop Q. Okay, so after that then we will do this. We use the answer from the previous index to answer this question, right? Prefix I will be equal to prefix I plus 1 no, I minus 1, right? If I minus 1 is actually larger or equal to 0, else 0, and then plus nums I, right? So that's for the prefix. So let's print it out to make sure it works correctly. Hit push. Okay. Hit push. Hit pop. Three, one. Okay, so here. Yeah, I think it's worked correctly. So 7 here, 16 here. Now we come here, we will remove this guy, that's 12. Come here, we remove two largest element, that's 12. Come here, we remove 3 largest element, that's this, and this, that's 6. Okay, so I think it works. Do another scan, but in the reverse way, right? And minus 1. Okay, so we need to reset our queue. Hit push queue. Now for the second half, right? So we are now doing the suffix, which is the answer for the second half, the second partition, right? So for the second partition, we need to maximize the total sums, right, of n element. So in order to do it, we need to continuously popping the guy with the smallest element out. So we need to do a min here. That's why we are pushing the nums at index I here rather than the negative number, right? Same as before. If n minus I is actually larger than suffix I. Now we do a minus, because whatever is in the queue is a positive integer, right? N minus I, is that right? Yeah, that's right. Okay, suffix I plus 1, if I plus 1 is actually smaller than n else 0 plus numbers I, right? Let's print the suffix, make sure it works. 3 to 2, that seems correct. So here 3, 4, and now come here, we need to pop this guy out, that's 11. Okay, here 13. Okay, so we will try out every partition point possible, right? So what is a validate partition point? So we cannot start from here, right? For this example, we cannot start from here because if we start from here, we are basically telling that the first partition only have one value. That's incorrect, because one partition must have n elements. So at the very least, right, we need to basically start from this guy, right? And then if we go too far, if we go up here, right, if we go here, so now the second part only has one value. So this guy is not a validate partition point also, so there's a bound, right? For I in range, we need to start from n divided by 3 minus 1, and we need to end at basically n divided by minus n divided by 3, right? So we take 6, we minus 2 from it, that's 4, so we are allowed to come here, right? 0, 1, 2, 3, 4, but the n in Python is exclusive, so at most we can come here, right? So that's correct. We need to define a variable called result, which we going to put if max means result prefix I minus suffix I plus n. Let's just return result. Okay, submit. It should be correct. As you can see, don't be fooled by the runtime. It's actually pretty efficient. As you can see, the complexity is actually O and log n, right? So we do a double scan, that's O n, but in each loop, right, we need to do a heap push and heap pop. The maximum number of elements in the queue should be n, so that's log n, right? So O and log n. So time complexity O and log n, and then the space complexity should be O n. Okay, so that's it for today. I hope you guys understand the solution, and see you guys in next videos.